Okay, we'll come back. Now, question is how these things are coming R into this thing. So, first equation is this VAB is equal to what you do here, numerator and denominator here you multiply by R, right. Then your VAB is equal to, if you multiply by R, it will be QA upon 2 pi epsilon 0 R minus your QB divided by 2 pi epsilon 0 R, then ln DAB upon R plus this term, numerator and denominator you multiply by R, it will be R into QC upon 2 pi epsilon 0 then R, right, ln your DBC divided by DCA, right. So, this is actually GA, this just now we have given, this is GB and this is GC. So, it will be actually R into GA minus GB ln DAB upon R plus R into GC ln DBC upon DCA, right. That means you take R common. So, it will be GA minus GB into ln DAB upon R plus GC ln DBC upon DCA. So, that what we are writing here, that VAB is equal to R into GA minus GB ln DAB plus this term. Similarly, VAC also same way you will get the same thing, easy to remember. Look, VAB is there, R is there, VAB. So, GA minus GB ln DAB R and other thing is the phase C. So, that is this VAB actually. So, phase first phase is GC ln DBC upon DCA, right. So, and similarly for VAC you can write R into GA minus GC ln DCA upon R plus GB ln DBC upon DAB, this is volt, right. Now, this next we will come to the phasor diagram, that we have to establish some condition. This actually we have seen in that capacitance chapter, and all things are detailed in given, everything is given there, right. If you those who have taken that course they know it, and those who have not taken this course I request them please go through that your capacitance chapter, everything is given, right. So, before proceeding further, look at this phasor. Suppose this is your VBC, this is VAB and this is VCA. So, using this make a triangle here, right. So, this is VBC, my VBC, and this is VAB, it is moving like this. So, VAB, so parallel, this is VAB, so make VAB. So, VBC, B is the, when you make AB, BC, CA and arrow tip, right. So, it is VBC. So, this you make as V for your understanding, and it is arrow tip VAB, A is fast coming, B wherever first your what you call that phase is coming, BC to BC means B phase, C phase, B is coming, it is B, AB. So, it is A, CA, arrow tips is here, it will be C, right. So, question is that this is your VBC, this is your VAB and this one VCA going down. So, VCA. So, this way first you complete the triangle, right, understandable, nothing is new I am doing, it is simple. This is VBC, this is VAB, make VAB and VCA, so make VCA, right. Then you assume the neutral point is there N. So, this is because of VBC arrow tip is here. So, it is B, VAB arrow tip is here for VAB. So, A and VCA, this is C. So, it is A, it is B, it is C. Next is this star neutral you make it, then this voltage will be VAN, this voltage will be VBN and this voltage will be VCN, arrow tip is here for AN, BN and CN here, right. Now, next on that, then if you then further I have not done, I will make it here for you. Now, suppose if you have this is VBC, this is your VCA, drawing may not be symmetrical, but understandable, but this is your VAB, right. Now, this is VAN, right. So, if you look into that VAB, BC, CA, if you look into that, and if you, that means this is your VAN. So, that is your VAN, this angle is 30 degree, right. This you know, right, this angle is 30 degree. Now, it is VCA, that means your VAB actually leading VAN by 30 degree, or VAN is your what you call lagging for VAB by 30 degree, and this is VCA. If you change this one, just opposite, it is VCA, then it will be your VAC, right. Then this angle also 30 degree, right. That means, if you take your VAN as a reference, for example, an angle between VAN and VBC is 90 degree, right. Angle between VAN and the way phasor is drawn, angle between VAN and VBC, it is 90 degree, right. So, if you that means, we have seen earlier that VAB and VBC is equal to 3 VAN. This is we have seen our capacitors chapter. So, question is that here also same thing, that if you take VAN as a reference, then suppose VAN is equal to VAN angle 0, right, then VAB will be root 3, because it is a phase voltage, it is a line to, it is a phase voltage, that is phase to neutral, and it is line to line voltage. So, VAB will be root 3 VAN. Suppose if you take, for example, if you take say VAN is equal to VAN angle 0 degree, right. If you take, suppose this is a phasor quantity, so VAN angle 0, so VAB will be root 3 VAN, but angle will be plus 30 degree, because it is leading. Suppose if my VAN is the reference, right, then VAB will be root 3 VAN, this one. Similarly, VAC, it was VCA, because we have taken 180 degree opposite, that is why VAC, right. VAC will be also root 3 VN, but angle will be minus 30 degree, because if this is reference, it is lagging, so it is minus 30 degree, right. Suppose it is understandable to you. So, similarly, that means, what we are doing actually, VN we have your taking as reference, say VN angle 0 degree, therefore, VAB actually root 3 VN angle 30 degree, this 16, this 17 equation number. That is why I have written, that is why VAB root 3 VN angle, this is you take as a reference, then only things analysis will be easier, right, and it is VCA. So, just 180 degree opposite, we have made change this polarity, it is VAC. So, similarly, then VAB is equal to root 3 VN 30 degree. Now, similarly, your VAC is equal to, I just showed you, root 3 VN angle minus 30 degree, this is equation 18. Also, for a balanced 3 phase system, if it is balanced, QA plus QB plus QC is equal to 0, this is known to you, right, and hence we are writing actually this one, we are what to call, just hold on, here I am writing, right. We know no, GA is equal to QA upon 2 pi epsilon 0 R, that means QA is equal to 2 pi epsilon 0 R into GA. Similarly, for QB, 2 pi epsilon 0 R into GB, and QC will be 2 pi epsilon 0 R into GC, right. That means, instead of QA, we can write 2 pi epsilon 0 R GA plus 2 pi epsilon 0 R GB plus 2 pi epsilon 0 R GC. Therefore, this 2 pi and epsilon 0 R is common, so it will not be there. So, GA plus GB plus GC is equal to 0, that means, for balanced system, if QA plus QB plus QC is 0, then potential gradient also GA plus GB plus GC is equal to 0, this is equation 19, right. Now, if you assume equilateral spacing, for a special case, say DAB is equal to DBC is equal to DC is equal to DC, therefore, equation 14 can be written as, right, I mean this equation, because all are same. So, I mean DAB, DBC, DC all are same. So, it will basically D upon D, this term will vanish, it will become 0, this term will vanish. Similarly, here also this term will vanish, for VAB basically this term will vanish, right. So, that means, in equation 14 it can be written as your VAB is equal to R into GA minus GB ln D upon R, this is equation 20, right. And we have seen that VAB is equal to root 3 VAN, your angle 30 degree, that you have seen. So, this VAB you can write that from equation 17 we have seen, it is VAB is equal to root 3 VN angle 30 degree, that is why writing from equation 17 and 20. is equal to R into Ga minus Gb ln d upon R. This is equation 21. Similarly, we can write VAC also, AB, BC, CA. So, VAC we have made it. VAC is equal to root 3 Vn angle minus 30 is equal to R Ga minus Gc ln dr, right. This is this right hand term, this is coming from equation 15. In that case, that third term will be, or what you call, will be vanished, right. Now, if you add these two, this root 3 Vn angle 30 and root 3 Vn angle minus 30, if you add these two, then you will get 3. I told you that VAB plus VAC is equal to 3 Vn, we have seen in the capacitor chapter, right. So, this if you add these two, it will become 3 Vn left hand side, right hand side will become 3 Ga R ln d upon R, or Ga is equal to Van R ln d upon R. Now, if you add these two, how I will show only the right hand side, that how things are coming, right. If you add these two, the equation 20 and 21 and 22, if you add, then it is coming actually, if you take R common, right, then and ln dr d upon R both are common. So, R ln d upon R, this is also common. So, in bracket it will be Ga minus Gb plus Ga minus your Gc, it will be like this, right. So, in that case, if you see that this is your R ln d upon R, right, and this will be 2 Ga minus Gb minus Gc. This one actually R ln d upon R, then you add 1 Ga, it will be 3 Ga, then minus Ga minus Gb minus Gc. So, this 2 Ga we are writing 3 Ga minus Ga, this thing, right, and it is minus Gb is there, minus Gc is there. So, it is equal to R ln d upon R. So, it is actually you can write 3 Ga minus Ga plus Gb plus Gc, right, but we have seen Ga plus Gb plus Gc is equal to 0. So, this term is 0, that is why it is 3 Ga R ln d upon R. That is why we are writing this one, that your 3 Vn is equal to 3 Ga R ln d upon R. So, 3 will be cancelled, and therefore, Ga is equal to Vn upon R ln d. This is equation 23. This is for phase A conductor, right, Ga, potential gradient. Similarly, Gb also similarly it will be like this, Vbn upon R ln d upon R, and Gc will be Vcn upon R ln d. But this is 24, very easy to remember, very easy to remember, right. Now, next is, so this is, I hope this is understandable to all of you, right. Next is disruptive critical voltage for a single phase transmission line. First we will consider single phase, then we will move over to 3 phase. So, the minimum voltage at which complete disruption of air occurs and corona start is called the disruptive critical voltage, right. This is the minimum voltage required, that it will be I mean air that there will be complete disruption of air surrounding the conductor, right, it occurs, and corona start is called the disruptive critical voltage. Now, the potential gradient corresponding to this value of the voltage is called disruptive critical voltage gradient. I mean, for this whatever potential gradient you will get for this condition, it is called the disruptive critical voltage gradient, right. Now, from equation 8, just hold on, from equation 8 we have seen that for single phase line, that V12 is equal to Q upon pi epsilon 0 ln d upon R. This is equation 26. The voltage gradient on the conductor surface is given by, from equation 10 only we have seen that is that maximum Gr is equal to G max, that is at the surface of the conductor, that is Q upon 2 pi epsilon 0 R. This is equation 27, or you can write Q upon epsilon your pi epsilon 0, you can write 2, just cross multiply by 2 R. So, Q upon pi epsilon 0 2 R G R, this is equation 28, right, and this Q upon pi epsilon 0 2 R G R you substitute in equation 26, here you substitute. If you substitute, that is I am writing from equation 26 and 28, we get V12 is equal to 2 R into G R ln d upon R, this is equation 29, right. So, the breakdown actually strength of air at the atmospheric pressure, that is 760 mm pressure, and temperature of 25 degrees Celsius is 30 kilovolt per centimeter. This is the maximum, this is the breakdown strength of the air. Now, you assume Vmax is equal to maximum value of disruptive critical voltage. Let us you define the Vmax is the maximum value of the disruptive critical voltage, and Gmax superscript 0, Gmax 0 is equal to maximum value of disruptive critical voltage gradient. Therefore, equation 29 can be written as Vmax is equal to 2R, Gmax 0, right, ln d upon R. So, this equation instead of V12 we will make this is Vmax, right. So, Vmax is equal to 2F Gmax 0 ln d upon R, but Gmax 0 is your 30 kilovolt per centimeter, which is equal to actually 3 into 10 to the power 6 volt per meter. So, that means Vmax is equal to 2R into 3 into 10 to the power 6 ln d upon R. So, this is the maximum voltage, right. So, these are your R, of course, R will be in meter, because we are writing it is volt per meter. So, R will be in meter. So, this is volt, right. So, this RMS value will be of this voltage, right, maximum disruptive critical voltage, it will be divided by root 2. So, the RMS value of the disruptive critical voltage for single phase line, V0 will be Vmax upon root 2. So, it will be 1 upon root 2 is equal to 6 into 10 to the power 6 R ln d, because this is 2 R into 3 into 10 to the power, so 2 into 3 is 6, that is why we are writing here 6 into 10 to the power 6 into R and divided by root 2 ln d upon R. So, this is equation 32. So, this is your what you call V0, that is that RMS value of the disruptive critical voltage, right. Next is disruptive critical voltage for a 3-phase transmission line. Now, let us define say magnitude Vn is equal to Van is equal to Vbn is equal to Vc, their magnitudes are same. This is equation 33. Now, we know this thing that Vn is equal to q upon 2 pi epsilon 0 ln dq by r. This we have seen, right, this we have seen. Now, where dq is equal to your what you call that dab, dbc, dca to the power 1/3. This is your, this we have seen in capacitance chapter, right. Therefore, we know this that q upon 2 pi epsilon 0 ln dq upon r, right. That means, in from equation 34 and 28 you will get. So, in equation 30, if you go back to equation 34 and you this and 28, this is your equation 34, this 28 is q upon pi epsilon 0 2 r gr, right. So, from this equation we get that Vn is equal to r gr ln dq upon r, this is equation 35. Therefore, that from equation 35 actually becomes this equation Vmax is equal to r g max ln dq upon r, because Vn is equal to Vmax, and if you put gr is equal to Gmax, because at the surface of the conductor or this thing, at the surface of the conductor potential gradient is maximum, that is at x is equal to r, right. Therefore, at that time in that case gr will be Gmax and then Vn will be Vmax. Therefore, this equation we can write instead of Vn we can write Vmax r, and gr should be replaced by Gmax ln dq upon r. This is equation 36a. I have marked it as 36a actually. Now, RMS value of the disruptive critical voltage for a 3-phase line, it is just divided by root 2. So, it is 3 into 10 to the power 6, because Gmax is 3 into 10 to the power 6 divided by root 2, then R, there is 3 into 10 to the power 6 your volt per meter, and R has to be taken in meter when you will solve the numericals. So, 3 into 10 to the power 6 upon root 2 R ln dq upon R, this is volt per phase, this is 36b, right. Now, next is that formula for disruptive critical voltage suggested by F.W. Peak, that is he has suggested something. So, based on experimental data, Peak suggested that the disruptive critical voltage is directly proportional to the air density factor delta over a considerable range. Therefore, a correction factor should be introduced for a calculation of disruptive critical voltage at conditions other than standard ones, right. Therefore, for a single phase line, the formula for disruptive critical voltage takes the form, everything is same, only delta is a delta thing is multiplied, right. So, the formula for this take the form V 0 is equal to 6 into, that is air density factor delta, right, 6 into 10 to the power 6 upon root 2, this is your RMS value, right, R delta ln d upon R. So, this air density factor delta has to be multiplied, right. For 3 phase disruptive critical voltage, same thing, that this thing, that RMS 1, that is your V 0 is equal to 3 into 10 to the power 6 by root 2 R delta ln d q upon R volt per phase, equation 38. Now, in equation 37 and 38, expression for disruptive critical voltage, it is assumed that the conductors are smooth and clean, that is surface is smooth and clean, no dirt, nothing is there. Based on that, this is for 3 phase, and equation 37 same thing, that is for single phase line. But conductor surface is rough and dirty, the disruptive critical voltage is somewhat less. So, in that case, to consider the effect in equation 37 and 38 must be multiplied by factor called m 0, known as, sometimes we call irregularity factor or surface factor or roughness factor. Okay, this value will be less than 1, right. So, 3 terms are there, irregularity factor, because conductor is not smooth, right, or surface factor or roughness factor, right. So, therefore, the mathematical expression for disruptive critical voltage can be given as V 0 is equal to same thing, 6 into 10 to the power 6 over root 2, earlier delta R delta was there, now multiplied by m 0 ln d q upon R. This is for single phase line, I have written here, this is equation 39. And for the 3 phase line, that V 0 will be 3 into 10 to the power 6 upon root 2 R delta m 0 ln d q upon R, this is equation 40. The approximate value of m 0 given by f w peak are as follows: m 0 is equal to 1 for smooth polished conductors. M 0 actually you can take in between 0.93 to 0.98 for rough and weathered conductors, right, and for m 0 is equal to 0.8 to 0.87 for stranded conductors, right. So, these are the some after after several testing other thing, he has made this kind of some range of this m 0 value, but in reality m 0 is equal to 1 may not be there, either this one or this one, right. Next one is visual critical voltage. This is actually, this is that visual luminous glow of corona generally occurs at a voltage higher than the disruptive critical voltage, right. So, we have to find that voltage. So, we have to see that actual visual corona does not start at the disruptive critical voltage. So, the corona which will be visible, that voltage is greater than the your disruptive critical voltage. For starting of corona, maximum value of voltage gradient is 30 kilovolt per centimeter, but this value of the voltage gradient at the surface of the conductor will not ionize the air, right. Therefore, the voltage gradient, that 30 kilovolt per centimeter, will cause ionization when this value is reached at a distance of some empirical formula R plus 0.0301 root over R from the conductor axis, right. So, this is actually something is suggested, right. So, that means R is that in meter, and the reason is that some energy is required by the charge ions to start corona, right. Otherwise, that is why this R plus in approximately R plus that 0.0301 root R, right. So, that some energy is required actually by the charge ions to start corona. So, if the maximum voltage gradient at the surface of the conductor say 30 kilovolt per centimeter, the value of the maximum voltage gradient in any other point, right, away from the center would be less than this, that is true, right. If you move away from the conductor, then naturally it will be less than that, and thus there will be corona discharge at that point. Therefore, the expression of the visual critical voltage for the single phase and 3 phase lines can be given as when the effects of irregularity of the surface of the conductor and air density factor are considered. These are to some extent is empirical formula, right. That means, this thing your what you call for a single phase line, that V we are giving, that visual critical voltage 6 into 10 to the power 6 upon root 3, then instead of you are making m v, this is another factor m v, then R delta in bracket actually what instead of r what we are making it r delta is there, but what we are making in bracket 1 plus 0.0301 root over r delta ln d upon r, right. This is an empirical formula actually, right. So, based on several field tests they have proposed. So, this is actually not coming from any derivation, these are we have seen, but this thing actually all through the field test, right. So, this is this way this formula can be written for single phase line. Similarly, for 3 phase line what will happen, that it will 3 into 10 to the power 6 over root 2 mb r delta is okay 1 plus 0. Only this term is changing, rest are same, only instead of 6 here it is 3, rest are same, right. mb r delta 1 plus your 0.0301 divided by root over delta ln dq upon r, this is equation 42, right. Where mb is the roughness or irregularity factor, for this case mb is equal to 1 for smooth conductor, mb is equal to 0.7 to 0.75 for local corona when the effect is first visible at some places along the line, and mb is equal to 0.8 to 0.85 for general corona along the whole length of the conductor, right. So, along the whole length of the conductor may be visible, but wherever little bit here and there I have seen, I have not seen this one, but localized I have seen it, right. So, the value of the voltage gradient G max at which complete disruption of air occurs is called the disruptive strength of air, right. That is, that value of the voltage gradient the G max at which complete disruption of air occurs, it is called disruptive strength of air. The breakdown strength of air at atmospheric pressure, right, and temperature, it is this thing, the breakdown strength of air, it is then is your 30 kV per centimeter in general, it is 3 into 10 to the power 6 volt per meter, this is the maximum, or 3 into 10 to the power 6 over root 2 volt per meter RMS value. So, value of G max 0 depends upon the density of the air, right. This value depends on the dielectric strength of air is proportional to its density over a wide range, right, and thus directly proportional to the your barometric pressure and inversely proportional to the absolute temperature. Based on that that air density factor, right, some formula has been proposed. I mean some your different field test or different testing, and there is no proof I cannot give you here, but some kind of empirical formula has been given. Thus, that air density factor at a barometric pressure of p millimeter of mercury and temperature say T degrees Celsius can be given as delta is equal to 0.392 p divided by 273 plus T. This is equation 43. Actually, this G max 0 depend on the your density of air, the dielectric strength of air is proportional to its density over a wide range, right, and thus directly proportional to the barometric pressure and inversely proportional to the absolute temperature, right. That is why this it is actually delta is proportional to P and delta is inversely proportional to 1 upon 273 plus T, that means delta is equal to some constant k into P upon 273 plus T. So, that k constant actually is 0.392, right. So, delta approximately is equal to 0.392 P upon 273 plus T. This is equation 43. Thank you very much. We will be back.